Measuring distances to faraway objects in the universe has led to two great discoveries in the past century. First, the expansion of our universe, and second, the existence of dark energy that is accelerating the expansion. The current standard cosmological model, or ΛCDM, which is composed of dark energy and cold dark matter, explains numerous cosmological observations in the past decade.
The current expansion rate of the universe, set by the Hubble constant, is a key parameter in this cosmological model. It can be either inferred from the observations of the cosmic microwave background, as the Planck and the WMAP missions did, or directly measured in the local universe.
In the Holy Cow and COSMOGRAIL collaborations, we make use of the power of gravitational lensing to measure the so-called time delay distances and the Hubble constant. To do so, we focus on systems known as strongly lensed quasars. Such a system is composed of a bright and remote quasar lying behind a massive galaxy. The gravitational field of the massive galaxy acts like a lens and distorts the light ray emitted by the quasar in such a way that multiple images of the quasar appear around the foreground lens galaxy. Since the light radiated by the quasar changes over time, we see the same flickering pattern in each of the quasar images, but delayed in time due to the different light path of the different images.
比如说，今天有4位朋友一起从台大出发到南港中研院，他们同时出发，但走不同的路线。虽然出发的时间一样，但是抵达的时间却不一样。抵达时间的早或晚有2种原因，第一种是路的距离长或短，第二是路况。
Similarly, the delay in strongly lensed quasar images depends on 1. the distance traversed by the quasar light ray, and 2. the gravitational delay of the lens. Since the distance traversed depends on the expansion history of the universe that is set by the Hubble constant, we can use this time delay between the multiple images to directly measure the Hubble constant. We use 5 of the best lensed quasars discovered to date to measure the Hubble constant. Our most recent one being HE0435, a bright, quadruply imaged quasar seen here with a Hubble Space Telescope. Using such images, we can build a model of the foreground galaxy mass distribution and predict how the background quasar looks like through this cosmic lens. The bending of the light rays depends primarily on the lens galaxy, but all the other galaxies along the line of sight between us and the quasar also have a small but measurable impact on the bending. Using several imagers and spectrographs on 10-meter class telescopes, we conducted a systematic identification of the galaxies along the line of sight to quantify their influence on the lens model.
Another key ingredient for the method to work is, of course, the time delays between the lens images. We have seen that the quasar luminosity changes with time, and so are the lens images. The optical path to each image is not the same and is affected by the shape of the lens, and this causes the quasar variations to be seen with a time delay in each quasar image. The goal of the COSMOGRAIL collaboration is to measure the time delays using the observed luminosity variations of the quasar images. To do so, we use several telescopes in the northern and the southern hemisphere, our main instrument being the 1.2-meter Euler Swiss telescopes located at La Silla in Chile. All facilities combined, we observe each quasar on average every few nights. This allows us to measure the time delays to a few % precision within a few years of monitoring. For HE0435, our monitoring campaign started 13 years ago, catching as many luminosity variations as possible for each of the 4 quasar images. These variations are turned into light curves where we can see by eye many similar features appearing at different epochs. These light curves are then shifted in time and in luminosity to match all the observed features and to measure the time delays. These delays are used in combination with the lens model to determine the value of the time delay distance to the lens.
The time delay distance depends on the parameters considered in our cosmological model. Its sensitivity is primarily on the Hubble constant, but it also depends very weakly on the composition of the universe. We combine the time delay distances to 3 strong lenses into a cosmological probe that we call the time delay strong lensing probe. For any given cosmological model, we can use this probe to constrain the value of the model's parameters. For example, if we consider the ΛCDM model, which is a flat universe with a dark energy in the form of a cosmological constant, we can combine the individual constraints from our 3 strong lenses and obtain a single value of the Hubble constant, around 72. This value is in excellent agreement with other independent measurements of the Hubble constant in the local universe that use the Cepheids distance ladder. The time delay strong lensing and the distance ladder are currently the most precise and robust techniques available to determine the Hubble constant directly. Yet, they are in significant tension with measurements from the cosmic microwave background observations in the standard cosmological model. One possible way to reduce this tension is to relax our assumptions on the cosmological model. Let's assume for an instant that the dark energy is something else than a cosmological constant, and that, technically speaking, it is described by an equation of state W different from -1. Now, if we plot the 95% credible region in the W versus H0 parameter plane, the constraints from Planck and WMAP will look like this. The constraints from the time delay strong lenses, on the other hand, looks like that. Combining the two, we end up with these credible regions, which deviates by more than 2 sigma from the cosmological constant assumption. In our work, we illustrate the power of the time delay distance of strongly lensed quasars as a cosmological probe, and we measure the Hubble constant with a precision of 3.8% that is highly competitive with and complementary to other direct probes.
Our time delay method holds great promise to measure independently the Hubble constant with 1% precision that is important for understanding our universe, including the nature of dark energy and neutrino physics.
Hundreds, if not thousands, of time delay lenses are expected to be discovered in upcoming surveys, and our current results pave the way towards an independent determination of the Hubble constant with a 1% precision and accuracy. Thank you for watching. You can find out more about our work at www.holycow.org.